One question I get asked a lot is whether or not you can use target sequence to solve for multiple burns in a profile at once. Well, obviously the answer is yes. You can give STK as many variables as you want and it will solve some burn profile for you. But there are a lot of caveats with trying to brute force your way through different solutions in RPO space, and I want to show you a use case where using a multi-burn profile like this inside of one target sequence that you then have STK try to solve for you simultaneously is actually to your benefit. Okay, so here is one such use case where multi-burn solving is to our benefit, and it's basically what I like to call max performing your satellite. So I have this satellite over here, 284 sat, that wants to move 1 degree. Now, the reason why 284 sat is named 2.84 sat is because it can only burn 2.84 meters per second in an hour. That is the max performance of the thrusters on 2.84 sat, and the question that we're going to try to answer is how quickly could 2.84 sat, if it was constantly burning 2.84 meters per second every hour, reach 1 degree away? Now, from our geo rule of thumb, we know that if we did 2.84 meters per second in track, we could get there in 24 hours. Piece of cake, right? However, let's see if we can get there in half that time, or 12 hours, using just 2.84 meters per second burns. Now, you might also remember from our geo rule of thumb, the radial burn, that it's about 13.4 positive radial to get there in a single burn. So using that number as our baseline, let's see how many 2.84 meters per second burns we would need to reach our target 1 degree away. And I'm going to use STK's target solver to answer this question for me. So the first thing I'm going to set up is, rather than using this RIC burn that we are typically used to, I'm going to transition my RIC burn to a spherical burn. So now I have azimuth, which is controlling radial and in-track, and elevation, which is controlling cross-track in a combination with radial and in-track. I'm going to set the magnitude of this burn to be 2.84 meters per second, and I'm going to relabel this burn as max burn. Okay, so now in any direction, I can only burn 2.84 meters per second. The next thing I'm going to do is add a target sequence, and I'm just going to name this target sequence max performance. And I'm going to throw max burn into max performance. And the variable that I'm going to be solving with is going to be this azimuth here. Now I need to figure out what my goal is going to be. And my goal is going to be arriving at this 1 degree point in 12 hours using only these max burns. So rather than have this set up as a duration, I'm going to set it up as an epoch. That way I don't have to constantly adjust the duration. Our scenario start time is quad Z. So I'm going to have this set for noon on the 4th of September. Sweet. So now what this target solver is going to do is going to take as many max burns as I give it and try to combine them in such a way that I arrive at noon. Have to set up this propagate so that it meets my end state. I'm just going to use in-track and radial because I'm already plane matched, so I will be at 0 kilometers cross-track already. I'm also going to throw range on here. And I'll show you why I do that when I show you one of the optimizers that I'm going to use to help me with this problem solving. Those are all set up to basic reference, which is going to be 1 degree. Okay, so now I'm going to call this goal, and we're just going to call it noon. And okay, so we know 13.4 is what it would take in a single burn. Let's divide that by 2.84 and see that at least we're going to need 4.7 burns. So I'm just going to add 5 burns to this target solver. And since I'm losing efficiencies with each of these burns, I'm just going to overestimate and add a 6 burn. Okay, so now I need to also add in the 1 hour propagates in between each of those, since I can only make these burns once per hour. Okay, so now I have 6 burns, all at 2.84 meters per second, and I'm going to try to combine them in such a way that I reach my target at noon. Let's go in here and set up the differential corrector that we're going to be using to solve. So first I'm going to turn on all of these different burns, and I'm going to turn on my arrival conditions, which is going to be 0 kilometers in track and 0 kilometers radial. I'm also going to turn on this arrival condition of range, And I'm going to set the tolerance for this such that it will never auto-fail the target solver. And don't really worry about this, but basically I want to set this tolerance to be greater than the distance I currently am. And the reason I want to add this variable is so that I can just see how the range is changing with each of these burns. Now the default when you give STK a azimuth to solve is going to be 30 degrees. That's going to be way too imprecise for what I'm trying to do here, so I'm going to set all of these to 3 degrees. That way it's not guessing like 30, 60, 90, 180, 30, 60, 90, 180 for each of these. It's going to be much more precise than that. Okay, tolerance is currently set to 1/10 of a kilometer. That's probably fine. And let's just go ahead and run this and see if we can get there. So now what you can see is it's going to take all these different azimuths and it's going to try to minimize the in-track and radial. And we can kind of watch its progress with this range here. So in 50 iterations, it wasn't able to converge. My recommendation, especially when you're working with azimuth, is to try to pick a number of iterations that is tied to the degrees of a circle. So for instance, 180 or 360. All I know though is this range number was still actively decreasing when it reached its 50 iterations. So I'm just going to apply some changes there so that all these burns get loaded with sort of the last solved value that they had, because we are still working towards what it looked like a good solution. Next, I'm going to add some more iterations. So let's just do 180. So half of a circle of azimuths will be checked. And let's just go ahead and start over. Still decreasing, still decreasing. We're getting to 27, 25, 24. Counting down. I might run this for a few more times, but I'm going to show you kind of a faster way that you can do this same level of problem solving. So let's just let it run, see if it'll ever get to a convergence. I'm suspecting we might end up a few kilometers short just by the fact that it wasn't able to automatically find a solution, but it's certainly getting lower and lower, so perhaps we will actually meet our estimate here. All right, so in 180, it still wasn't able to get to that target, but it did get within 10 kilometers, which is pretty close. It was still decreasing at the time that we hit this final burn at 0,500. So what I want to do is add in an optimizer to see what was the closest we possibly could have got, and then pass that information to a differential corrector. So Target Solver has all of these different profiles it can run. The one that I'm going to do is an interior point optimization algorithm. Don't even worry about what that is, but it just unlocks a different way for STK to problem solve rather than just doing differential correcting, which is essentially a guess and check method. Using basic kind of Newtonian calculus. So I'll get rid of my differential corrector here. Unfortunately, I'm going to copy it first before I get rid of it. And I'm going to move that down to be below the optimizer because I want the optimizer to be the first thing that's going to run here. All right, so what is this optimizer and what is this going to provide me? So this optimizer can use all of those same variables. So I'm just going to turn those on. And now instead of setting for a solution, which the differential corrector is designed to do, I can set for a goal. And in this instance, rather than using a bound, I'm going to use a minimize goal for the range. So what this optimizer is going to do is it's going to say, I'm going to take all these burns and I'm going to combine them such that this number gets to a minimum. And it will essentially search forever trying to find what is the lowest possible value. And by default, it'll go through 3,000 different iterations. Unfortunately, my laptop isn't nearly good enough to solve that many iterations in a time that would make this YouTube video palatable. So I'm just going to do 3 iterations and we'll kind of see how it does its guess and check method. After it goes through its solutions, I know it's not going to solve because it'll never find a perfect solution in only 3 profiles. So I'm going to go ahead and select this to continue profiles don't converge. What that means is the optimizer will take its best guess and then it'll pass it to the differential corrector with all of the updated burns. The differential corrector will get its best guess, and then it's going to pass it to the next differential corrector. Now in my final differential corrector, I want to give it a little more precision. So rather than 3 degrees to solve, I want to go down to 1 degree. And I know I'm only off by about 10 kilometers with our first method. So let's just see if the combination of these 3 methods can get me to a quick solution. The optimizer is really good at looking through all of these variables and minimizing this number very quickly, much faster than the guess and check differential corrector. So let's just see how this works. So here's the optimizer running, and it's just going to try to combine all the factors until it gets to the lowest number it could find. Okay, in 3 runs, it wasn't able to get it much lower than the original differential corrector, but it gave it very good values, which you can see where our range is now flirting with 0.1 kilometers. So we're almost within the constraint here. We might just be half a meters per second short on what we can provide. So it's going to run through its 180 different sequences, trying to find that perfect number. And then we're going to find out in the next solver is if this 3-degree constraint that this is, as you can see, 46, 49, 46, 49, etc., 43, that might be too imprecise to actually dial in this last level of tolerance that we need. So it will take its best guess values and it's going to pass it into the next differential corrector, which may have the precision needed to actually meet this tolerance here. Oh, we are so close. Okay, now we're in our final differential corrector. It has much more precision, and sure enough, it was in fact the 1 degree, the 3 degrees of precision that the second one had just wasn't enough for us to get there. So there it is, the combination of 2.84 meters per second burns to get us there by noon. Now from here, we were able to do that with only 5 burns, and we still have 7 hours before noon. The next logical question is, okay, well, could we have gotten there in 10 hours? Could we have gotten there in 7 hours? Could we have gotten there in 6 hours? So normally what I'll do here is I'll just back this goal down. Let's just say, can we do this in 10 hours? I know that that's probably going to require at least 2 or 3 additional burns, so I'm just going to add them now. We'll get some extra hours in between those burns, and let's just give this problem to the differential corrector that we've set up and see what it can make of it. First, we have to go in and turn on those new burns that we provided the system. And since I'm giving it a new problem to solve, I'm going to give it 5 guesses with the optimizer just to try to dial down a little bit faster. And we have to go into each of our differential correctors and turn on those new burns. So here we have the 3 degree brute force method, and then we have the 1 degree brute force method at the end. Just because I'm a little impatient, that 180 iterations of solving just wasn't running fast enough for me, so I'm going to back that down to 90 and 90 here. And okay, now we're trying to get there by 1000, and we'll be burning all the way out to 0800 and see if we can get there. There's the optimizer trying to combine all of these different parameters to see how low it can get this value. It's going to run through this optimization algorithm 5 times instead of 3 times. So here's its 4th run. We're getting down to 86 kilometers. The reason why I don't allow the optimizer alone to solve this problem is it's not really good at finding the end state. It's only good at finding sort of constraints and bounds. So there we were able to get to 70 kilometers. Let's see if the differential corrector can knock that number any lower. While this is solving, I'm closely watching this range here to see if it's essentially plateaued on all of the guessing that it's doing. It doesn't look like we're going to be able to get much closer than 79 kilometers with the amount of delta V we've provided the system. It's only going to go through 90 iterations here, so we may as well let it go to the next sequence. But it looks like I'm at least 2 burns short when it comes to meeting this goal of arriving at 10. So now we have the high precision differential corrector running through with its 1 degrees of tolerance. And sure enough, it's not really getting much better than that 79 kilometers that the other values were passing. So I'm going to go ahead and stop it. And now we've run into the age-old question of this burn occurs at 0700, which is only 3 hours before we reach our 1000. So at most I have 2 more burns here. We may as well just add both of those burns now and see how close we can get if we burn all the way out to 0900. So now we have a sequence of 9 burns, and we're going to try to reach it at 10 o'clock. We have to go into each of our different scalars here and turn on those values. So now we've added it to the optimizer. We'll add it to the 3 degree brute force, and we'll add it to the 1 degree brute force. Okay, so now we're burning all the way out to 0900, and let's just see where we can go. So let the optimizer run first. It's only going to go through 5 iterations. Not super promising so far. It's really only knocked off about 9 kilometers. Okay, a little bit better. We're down to 60 kilometers. It's about to give up because this is its 5th iteration. So it was able to guess this all the way down to 58 kilometers. Let's see how the brute force does. Okay, it beat the optimizer. It's moving down under 50 kilometers. And it looks like it might plateau right about 50 kilometers. So with this level of precision, it was only able to get us down to 50 kilometers. The additional 1 degree of freedom might get us another 5 kilometers max out of this. But I would say it's probably just not feasible to combine 2.84 meters per second burns to reach a target in only 10 hours. We will at least let this solve to see how close we could get. And we'll see if the 1 degree of freedom can get us a little bit more precision. So 50 kilometers is the number to beat, which is what the brute force 3 degrees of freedom was able to solve for. Let's let this run and we'll see where it gets. So it looks like for all of the solvers, 50 kilometers was about the best that we were able to do, using burns all the way out to 0,900. Normally what I like to do here, even though I've basically dialed in the max performance of the system, it looks like about 1030 is the best that you can do if you combine a bunch of 2.84 meters per second burns. There's kind of 2 ways we can find the final goal. We can let this vary out to, say, 1030 and see if it, because we know that 1100 works. We know that 1200 works. 1000 apparently doesn't work. So what number do we need to set here so that these sequences of burns can actually reach the target? So you could just make that a new variable and then let it solve out to between 10 and 11. So we'll run through that exercise. Sometimes I might also just come in here and turn on the magnitude of this burn to see how much extra oomph did I need to get there. And you can change any of these burns. So let's just say that 2.84 was an underestimate for the performance of our system, and we actually had 5. It's pretty reasonable to assume that, especially in these early burns, if we threw 5 meters per second in instead of 2.84 meters per second, we probably could have got there in 10 hours. Let's just go ahead and see what STK thinks the optimal time for arrival is. So we'll go back into our differential corrector. Here for the stopping conditions, I'm going to let this go from 10 to 1100. We're going to scale according to, let's just say 5-minute intervals, because we don't want to sit here and watch this all day. So let's just do 6-minute. So now it's just going to look through each of these 6-minute intervals and try to find what was the optimal time. We'll go in and change the other differential corrector. So we'll add that as a variable for this one. And let's just go ahead and see what we can do here. Looks like it likes 1030 here as one of its first hacks. And by 1024, we were at 10 kilometers. So just let it continue to solve this out. 1031 got us to 2.7 kilometers. We're almost out of iterations for the optimizer before the actual target solver will get its say. We got to 1 kilometer by 1030. We got to sub-kilometer at 1029 in 47 seconds. Okay. So the optimizer is going to continue to do its thing. I think this is its final run, and then it's going to kick it to the differential corrector where we can finalize this value. And there we have it. We were able to actually solve. Let's see what it thinks the optimal time for arrival is. 10:24 and 51 seconds. Okay, so there you have it. If you have a 2.84 meters per second constrained satellite and you want to know what is the absolute fastest max performance it could reach 1 degree away, apparently 10 hours and 24 minutes is the best you can do for 1 degree. Now, when I say best, there's a lot of other things that we could optimize along this route. The amount of free fly that we have in between these propagates is currently set to 1 hour, but there may be a combination of free flight plus burns that actually outperforms the profile that we have right here. But in just under 15 minutes of letting STK do its thing, we now have found that for 2.84 meters per second constrained satellites per hour, about 10.5 hours is really the best you can hope to do if you want to move 1 degree. You could use all of this same steps with a 1 meters per second constrained satellite or a 10 meters per second constrained satellite, just letting these different target solvers solve the problem. I just wanted to show this to you guys as kind of a baseline, and you guys can take it from here for your own experimentation. Thanks a lot for watching. See you next time.